So here's the idea. We don't know much about the closed interval, but we do know that it's connected and compact. And if you reflect on other times the interval has played a special role in this course, really those are the two key features we use about it so far, and that it's linearly ordered. So in other words, every element determines a subset of it, namely everything less than it. So we'll consider all those times t such that there is a unique filler, maybe not from time 0 to time 1, but from time 0 to time t. So consider, or let z be the set of all t's in the interval such that there is a unique filler up to time t. And including t. This is gamma restricted to the interval from 0 to t, so such that there exists a unique thing like that. That's a subset of all the t's of 0, 1. What we'll do is argue that z is non-empty and both open and closed. Then using the fact that the closed interval is connected, that'll give that z is entire. And by definition of z, that would mean that there exists a unique lift. So this is some kind of induction. It's just like a continuous version of induction. Notice that 0 belongs to z, therefore z is not empty. Indeed, 0 belongs there because the closed interval from 0 to 0, which is just 0, does have a unique lift, because it exists because it's already been chosen, and it's unique because that downward map, in this case, when t is 0, is bijection. So next, claim that z is open in the interval. Well, to see that, so we'll show that for every element of z, there's a little open neighborhood in 0, 1 containing that element and entirely contained in z. So let t belong to z. Now choose a neighborhood about the value of the path at time t, and b such that there exists a phi. Phi is a homeomorphism between u cross pi inverse of gamma of t and pi inverse of u over u. You know such a u exists by definition of a covering space. And I say that there exists a homeomorphism phi, so choose one. So there's where we use the map pi as a covering space. How does that help us? Well, gamma continuous implies there exists an epsilon greater than 0 such that the interval between t minus epsilon and t plus epsilon is carried by phi, or by gamma, into U. Because U is open. So, so now I'll write this out diagrammatically. I don't know if you can see that. Okay, so we have this diagram already. Now, what is this diagram? Well, gamma is a map from the interval to B, and we can restrict that map to this little interval, open interval about our chosen t that we chose, so that gamma of it belongs or lies factors through this open U. So gamma carries this interval inside of U, inside of B. And by definition of Z, there already exists, we've already established a unique lift here from the interval from t minus epsilon to t, including t, into E. But because this factors through U, this lift factors through pi inverse of U. Pi inverse of U is homeomorphic via phi with U cross pi inverse of that singleton. So phi implements this map, and we get this commutative diagram. But now, think about what this map is. We're mapping to a product topological space up here, and a product topological space has the feature that a continuous map to it is a continuous map to each factor independently. So if we're trying to establish that there exists a unique lift like this, that's to show that there's a unique such map to U. Well, it has to be just gamma, okay? And there's a unique map to this factor compatible with the already established one. But this is a discrete topological space. This is connected. Any continuous map from a connected topological space to a discrete one has the feature that it's constant. So any such map into this product, making this bottom triangle commute, is simply the data of an element in this discrete topological space. And such an element has already been selected. It's the value on T. So there does indeed exist a unique continuous map making this diagram commute. I feel compelled to draw a picture. So let's say U looks like that. U cross a discrete space looks like this. possibly infinitely many parts. This little interval maps by gamma into it, maybe selecting out that. There's this half open interval. And we've already established, essentially by some kind of continuous induction, a gamma tilde up to that point. It's defined up to and equal to t. That's a less than or equal to t as the subscript. So that looks something like this. And we're wondering now, is there a continuous map from the interval into this yellow stuff that on the one hand extends the already established map, and on the other projects down by pi in the way compatible with the original gamma. And there is a unique such way. It has to select out this factor. You cannot have it go into here. That would be discontinuous because these are disconnected and that's connected. So it has to go into here, but this just projects home, that slice projects homeomorphically to this version of U, and this map has already been specified, so it has to just look like that. So that's a picture version of what's up there. So that verifies this claim that capital Z is open. To see that capital Z is closed is essentially the same argument. I'm just going to erase little bits. So claim that is not open now, but closed. So let's not select t in Z, but select t in the limit set Z prime. And do all the same stuff, make exactly all the same choices. But now here, it amounts to the same argument, but where I changed things very so slightly just to put it open there. And the exact same argument works. That's just open now, and this is open, which changed nothing in the argument. So the proof that Z is closed is essentially the same as the proof that Z is open. So Z is both open and closed. It's non-empty. That means it's a union of connected components, a non-empty union of connected components of the closed interval. But the closed interval is connected. So finally, since the interval is connected, then Z is entire. And that's what we wanted to show, that there exists this lift on the entire thing.